So let's start with the number system that we're all most familiar with, unless you're an alien, and that's decimal. Now I want to introduce a concept called base, or radix. Radix is Latin for root, and base is basically root as well, right? Now the base, or the radix, is simply the number of digits that the number system has. Decimal has 10 digits. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Now there are other number systems that have a different base. Base 2 is called binary. Base 12 is called duodecimal. Base 60 is sexagesimal. Base 16 is hexadecimal, and base 8 is octal. And maybe you'd have to invent one for base 785. Let's call it base crazy. But going back to base 10, what does this really mean? If we take a typical number, like 123, what we can observe here is that as we move from right to left, the number is talking about increasing powers of 10, increasing powers of the base. To explain this clearly, so we'll say that the number in this position is 10, which is the base, raised to power 0, multiplied by this, multiplied by the digit. So 10 to the power 0 is 1. Anything to the power 0 is 1. If we go along to the next digit, it becomes 10 to the power 1. 10 to the power 1 is 10. And we're obviously very familiar with this concept that this is 20, right? So it's the two tens. So that's the number of tens. As we go further over to the left, we have 10 to the power 2. Just in case somebody isn't familiar with it, when we raise to the power, 10 to the power 2 will be 10 times 10. And 10 to the power 18 would be 10 times 10 times 10 times 10, 10, dot, 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 18 times. So we can put whatever we want there as a power. So that's the number 123 expressed in multiples of powers of 10. And we're so familiar with this that we don't really think most of the time about this being expressed in multiples of the power of 10. But when we want to talk about different number systems, it makes a lot of sense to think of it like this. So now let's look at the binary number system. Now the binary number system, as the name indicates, has two states. It has two digits. It is base 2, or radix 2. The digits are of course 0 and 1. But this is absolutely comparable to the decimal system that has 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So how do we write a binary number, and what does it mean? Well, we do the same as we did for the decimal system. If I start on the right, so what does this number correspond to? The number 101 in binary. Well, let's break it down. So the rightmost digit is 2 to the power 0, is multiplied by 2 to the power 0. 2 to the power 0 is 1. So this is just 1, okay? So we've got 1 plus, then the next digit, we multiply by 2 to the power 1, which is just 2. Oh, 2 times 0 is 0, so that doesn't add anything. And then the next digit is 2 to the power 2, which is 2 times 2 is 4. And we've got one of those, so plus 4. So this number, 101, in binary, represents the number 5. Hopefully you can see the direct comparison there between the decimal and now binary. The reasoning we followed for both decimal and binary is true for any base. So for any base, we're always increasing by powers of the base as we move from right to left. So to make that explicitly clear, if we want to express a number that has n digits in base b and calculate its value, we do the following. So we'll represent our number having n digits like this and index it from right to left. D1, D2, D3, dot dot dot, that just means I don't care about these ones, Dn. So that's our number, there are its digits. How do we calculate its value? Well, we do the following. Now we're assuming it's in base b. So we start with b to the power 0 times the first digit. Then we add b to the power 1 times the second digit. Little times in there. Then we add b to the power 2 times the third digit. I'll put the dots in, and we end with b to the power n minus 1 times the nth digit. The reason it's n minus 1 is if you look, we start at 0. So the first digit is 0, the second digit is base is raised to the power 1, the third digit base is raised to the power 2. So we're always raising to the lower, to 1 less than the digit index as we proceed from right to left. So for the nth digit, we raise it to n minus 1. So that's how you generally calculate the value of a number in any base. Let's do another example. Let's look at hexadecimal. And this is base 16. It's beginning to sound complicated, but it's just the same as before. Now base 16 has 16 digits. But wait a minute, what comes after 9? Well, the digits for base 16 are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then A, B, C, D, E, F. So let's examine a base 16 number and work out what it actually is. So say we saw a base 16 or a hexadecimal number that was F3. Now what is F3? Well, we proceed as before. The digit on the rightmost is the base to the power 0, so that's just 3. The digit to the left of that is the base to the next exponent, so we just times F by 16. Now F was the 15th digit in our number system. So starting from 0, going through, A was 10, B was 11, C was 12, D was 13, E was 14, F was 15. So we've got 16 to the power 1, which is 16, times F, which is 15. So 16 times 15 is 240. So 3 plus 240 is 243. So F3 equals 243 in decimal. So that's how we would examine a hexadecimal number. I hope you can see by now that actually working in different bases is not that different from working in base 10 and is not that difficult. In the same way that we have methodologies for things like long division and addition, where we line the numbers up above each other, for decimal there are similar methodologies for binary and even for hexadecimal. We're going to talk shortly about hexadecimal and binary numbers again because they're really important in computers. But before we do that, first of all I'd just like to examine something about the properties of different number spaces, and that is how many different numbers for a given number of digits can be represented. So to make that very clear, I'll give an example in decimal. So say we have 5 digits, a 5-digit number in decimal, 1, 2, 3, 4, 5. So that's 12,345. In our 5-digit space, what is the largest number that we can represent? Now, most people, you'll know actually that it is 99999. So 99,999. That's the largest number we can represent with 5 digits in decimal. How many different numbers can we represent? Well, we actually have 999,999. So we've got all those numbers, and we've also got 0. So that's actually 100,000 different numbers we can represent with 5 digits. So what's the maximum number we can represent with 5 digits? Well, we already know what it is, but let's go through the reasoning so we can then generalise it. Well, we know that we'll fill it up with 9s. And if we add 1 to this, then it will spill over into the next column, which is 10 to the 5. So what this tells us is that actually the maximum number we can represent is just 1 less than this, which is 100,000. And that's always going to be true. So no matter how many digits we've got, if we fill it up with 9s, that'll be the maximum number. And then if we add 1 to that, it will spill over into the next column. So if we subtract 1 from this number, that gives us the maximum number. So 100,000 minus 1 is 99999. And from what we said before, the number of different numbers is actually that plus the number 0, so it's actually 100,000, so it is just this. So how could we work out what this number is going to be for the number of digits we've got? Well, if we've got 5 digits, then we start at index 0, so at the end of our digit sequence we're going to be at 4. We're going to be at whatever our number of digits is minus 1. And then the next one is going to be this plus 1, which in our case is 5, which is actually just the number of digits. And it's always like that because we always index at 0, so no matter how many digits we've got, this is always actually just going to be the number of digits. So we can say then generally that if we want to work out what the maximum number we can store is for a base b and number of digits d, then it's going to be base to the power d, number of digits, and that will give us this number. And then to get the maximum number, it's just base d minus 1. So for base b and d digits, the maximum number we can represent is base to the power d minus 1, and the number of different numbers we can represent is always that plus 1, because we've got the digit 0, so that's just base to the power d. So that's how you can calculate for any base what the maximum number is you can represent in a given space, and also what the largest number is. And it's easy for us to see what the largest number is in decimal. We can see that it's 99999, we can already tell that. But when you look at a number in, say, hexadecimal or binary, and it isn't immediately clear, unless you're familiar with how the powers of 2 add up or the powers of 16 add up, what the maximum number is that you can represent. So you can just calculate it like this. I'd like to take a closer look at binary and hexadecimal numbers, because they're used frequently in computers. One of the reasons for this is because one of the primitive data types in computers is called the byte. So that's B-Y-T-E. And this is 8 bits. A bit is a single binary digit. Let's write out a typical number. I'll just pick one out. A 8-digit binary number. Let's have 01010101. So a byte with its 8 bits can actually represent 2 to the 8 different numbers. That's 256. And the largest number it can represent, if these are all 1s, is 1 less than that, is 255. And in order to calculate its value, let's proceed as we did before. So I need the powers of 2, which is the binary's base. Starting from the right, we've got 2 to 0, 2 to 1, 2 to 2, 2 to 3, 2 to 4, 2 to 5, 2 to 6, and 2 to 7. it's useful to actually write out what these values are. So 2 to the 0 is 1, 2 to the 1 is 2, 2 to the 2 is 4, 2 to the 3 is 8, and I think you can already see what's happening here. We're actually doubling each time, multiplying by 2 each time we go up a step. And this is similar to the way that we multiply by 10 each time we go up a digit in decimal. We always multiply by the base, essentially. So this is 16, 2 to the 5 is 32, 2 to the 6 is 64, and 2 to the 7 is 128. So what is this number then? Well, let's do the addition. Or we may as well do it from left to right, actually. So we've got none of these, we've got one of these, so we've got a 64 plus a 16 plus a 4 plus a 1. That's it, right? So what does this number add up to? Well, that's 80, 64 and 16. That's 5, so it's 85. So this number is 85 in binary, and that's a byte. Let's now look at the relationship between binary and hexadecimal numbers. What's interesting here about binary numbers, and about any number system actually, is that we can break this up into two blocks. So this 4 over here, and this 4 over here. And if we look at what this number actually represents, this is 5. We looked at it earlier actually. It's 2 to the power 0 is 2, plus 0 of 2 to the power 1, plus 1 of 2 to the power 2 is 4, so 4 plus 1 is 5. So we know that this represents number 5. And we know that this number is the same, if we just looked at it like that and ignore the rest of the digits, is also 5. So is there a way we can compute the value of this without having to do all the calculations for everything? And in fact, this allows us to make a shortcut. Now let's look at this by analogy to the decimal system before we look at this. If we had a number, say 5050, we could also break this up into two separate 50s. Or we can see what they are. That's the thing with the decimal system, whereas 0101 we have to work it out to see that it's 5. But that's just the way we represent it. You might look at 101 like I do now, I've seen it so many times, and I see 5. Now, if we want to calculate what this number is, we know it's 5050, but if we want to calculate it using the exponents of the base, we could go along and do 10 to the 0, 10 to the 1, 10 to the 2, 10 to the 3, perform all the multiplications, and then perform all the additions thereafter. But what we could also do is realise that actually we know that these two numbers, the largest number they can represent, there's 2 digits, so it's the base to the power 2. So the largest number of different numbers they can represent is 100, and the largest number they can represent is 99. So what this means is that each digit that rolls over in here represents 100, right? It's 10 to the power 2. So we can think of this being 50 times 100 plus 50. That might seem a bit cryptic and obvious, but let's go back to the binary system. If we do the same thing and we want to work out what this chunk is actually, what we're actually saying there, because we can look at this, and once we're familiar with binary, we can see that 101 means 5. So immediately that block of 4 bits looks like 5. But what can we say then 5 times something plus 5 is the number that we're looking for, is the value of this number? Well, if we do the same as we did for the decimal, and now you'll see why I did the decimal analogy, if we start here with this being 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, then this digit here is 2 to the 4. So we know that essentially each count in this block is 1, 2 times 2 to the 4. 2 to the 4 is 16. So we actually have 5 times 16 plus 5. 5 times 16 is 50, plus 30 is 80, plus 5 is 85, which is what we worked out before. What you can observe here, and which is really important, is that we were using 16. That's because we were looking at blocks of 4. And this is why hexadecimal becomes very useful, because hexadecimal is base 16. So what that means is we can actually succinctly represent each of these 4 digits in base 16. 5 is just 5 in base 16. And 5 is just 5. So in base 16, by the way, we usually subscript the base if we're talking about different bases. So just write it down in the bottom right. So 55 in base 16 is equal to this in binary and is equal to 85 in decimal. But this is a lot more compact and easy to read than this, which is why people use hexadecimal, because you can easily understand the value of a number, of a binary number, quite quickly. You'll see something like this. You've probably seen this before, even if you're not familiar with computers. You may have just seen that somewhere. And this would be f, which is 15 in hexadecimal, and 15, this would be the binary number 1, 1, 1, 1, 1, 1, 1, 1, where this f is these 4 numbers, and this f is these 4 numbers. So that's the relationship between binary and hexadecimal numbers, and it allows you then in programming and in reasoning about numbers to use something that's a lot more succinct and easy to kind of reason about and easy to write down in a clear way than writing out the whole binary number. So that's all I want to say really about computer systems today. I may go into binary addition and multiplication and so on in another YouTube video. If people are interested, there's quite a lot of documentation out there already. To end this video, let's just think about some other number systems. So duodecimal, base 12. Now, so this would have the digits, well, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. That's only 10 digits, so we need 2 more. So we could use A and B. We'd use whatever we want. And if I were to say to you, I have that many donuts in base 12, how many donuts have I got? Well, I've got 1 times 12 to the 0 is 1. Because 12 to the 0 is 1. Plus 1 times 12 to the 1 is 12. So 1 plus 12 is 13. So I actually have a baker's dozen. And in some way this is quite elegant and amusing because this looks like an 11. Our base is 12 and it represents 13. So there's some kind of odd sequence there. But you can see actually that you're probably already familiar with base 12, even though it's kind of seems like a crazy number system to be talking about. Because if you're talking about dozens, if I say I've got 5 dozen of something, then what I really have is that in base 12. So for the last number system we're going to look at is base 60. Now this sounds completely insane, right? Base 60. The Sumerians actually used base 60. And historically, there's been quite a few civilizations that either used base 12 or base 60. And believe it or not, we still use base 60 quite often. If I were to say that there'd been 17 hours, if I was just to 5 minutes and 27 seconds or if I were to show you a time like that, you would immediately know what it means. But this is in fact base 60, because there's 60 seconds in a minute, and there's 60 minutes in an hour. Unfortunately, there's not 60 hours in a day. We'd have to come up with some other term to mean 60 hours. But for the first 3 digits, it is base 60. And we reason in base 60. It's quite hard to add times together, because that's the equivalent of adding in base 60. But we've become reasonably good at it, to say, in an hour and a half from now, we can do the kind of mental arithmetic in our heads for very simple calculations. For more complicated calculations, if I were to say add 1705.26 to 607.21, it would be a little bit more complicated. But I just wanted to illustrate that we actually use base 60 in our day-to-day lives. Just a final thing to say about 1705.27. Whilst this is in base 60, we're obviously using decimal numerals to represent each of these digits. This is actually only 3 digits in base 60. So this is 1 digit, this is the 2nd digit, and this is our 3rd digit. The Babylonians had a number system for this. So I'll draw out what this actually looks like in Babylonian. So there along the top is 1705.27 in Babylonian. Pretty useful. You can see that I spend my time doing very useful things. Well, that's all I want to say about number systems. Hopefully this has served as a useful quick introduction to the fact that we use and there exist different number systems in different bases other than decimal, which we're all familiar with. Okay, I hope that was useful. Cheers.